Hello everyone, this is Shran from LearnAcon with another video from the Fundamentals of Industrial Automation series, where we explore the core concepts and technologies that form the foundation of modern industrial automation and control. If you are interested in building or expanding your knowledge in this field, I encourage you to subscribe to this channel. Today, we are diving into PID Closed-Loop Control. This is an essential topic that every automation and control engineer needs to understand. We explore the key elements, review how they influence the system's behavior, and look at some real-world examples. Okay, let's get started. Let's begin with the basics. PID control is a method used to automatically regulate systems, like keeping a motor at constant speed or maintaining room temperature. It's called PID because it uses three components: proportional, integral, and derivative. Together, they form a feedback loop that continuously adjusts the system to reach a desired target. PID is widely used in several industrial automation and robotics applications to control system stability and accuracy. Here is the heartbeat of a PID loop. On the input side, a PID loop compares the desired value, called the setpoint, with the actual value, known as the process variable. The difference between them is called the error. The controller uses this error to calculate how much correction is needed. It then sends a signal to an actuator, like a valve or motor, to adjust the system. In simple words, it compares what we want with what we've got by calculating the error and uses three strategies, P, I, and D, to fix it. Next, we will have a closer look at each of these three elements. First up is the proportional term, or P, which is the simplest. This term tackles the current error, the difference between your desired setpoint and the actual value. For instance, if your room is 10 degrees too cold, the proportional term tells the heater to blast more heat. The P is like a reflex. It reacts instantly to the error. The bigger the gap, the stronger the push. It's like pressing the gas harder when you are far from your target speed. But using only P can leave a small lingering error, called steady-state error, where the system never quite hits the mark and cannot eliminate the error entirely. It is fast, but not always precise. That's why we need more than just P. Next is the integral element. The integral term looks at the history of the error. It adds up past errors and increases the output until the error is gone. This helps to eliminate a steady-state offset, but if tuned too aggressively, it can cause overshoot or instability. In simple words, integral control is the memory of the system. It remembers past mistakes and keeps nudging until the error disappears. But keep in mind that too much memory can lead to overcorrection. Last but not least is the derivative part. Derivative control is the fortune teller. It predicts where the error is heading. It looks at how fast the error is changing and reacts based on that. If the system is approaching the setpoint too quickly, it slows things down to prevent overshoot. It's great for stability, but can be sensitive to noise in the signal. So far, we've learned how the P, I, and D behave individually. Now, we need to figure out how to combine these elements. That's done by something called tuning. Tuning a PID controller means finding the right balance between these three terms. The goal is to make the system respond quickly without overshooting or oscillating. You can do this either manually or using proven methods like Ziegler-Nichols. Tuning is where the magic happens. Adjusting the gains is like seasoning a dish. Too much or too little can ruin the flavor. The goal? Fast, accurate, and stable response. PID controllers are everywhere and used in countless applications. From controlling the heat in industrial furnaces, keeping your car at a steady speed, to stabilizing drones in flights. Their ability to adapt and correct makes them essential in modern automation. PID controllers are the champions of automation. They quietly keep things running smoothly behind the scenes. Okay, this was a quick overview of PID closed-loop control. I hope you learned something new. If you found this video helpful, please give it a like, share it, and subscribe to the channel for more similar content. Thank you for watching and see you in the next one.